I would like to start by thanking ITU for giving us this opportunity. Morning, afternoon, and evening to everybody, depending on where you are. Today, as Thomas has already told you, I'm going to talk about two areas. One is privacy preserving remote medical diagnosis. The other one is resource and specifically spectrum allocation for intelligent use of the available spectrum resources. So let me just start the presentation and then I will continue to introduce the topic a little more. Uh, so, So is the presentation visible to everyone? And I'm on the first title slide.
Yes.
Is that correct, Thomas and Vishnu? Yeah, okay, thank you so much. So, so like I was saying, today we are going to cover two of the five challenges that we have in the India part of the challenge. The first one is on AI techniques for privacy preserving remote medical diagnosis, and the other one is on spectrum and network resource sharing. In the last presentation, I had focused on computer vision centric applications. This time we're going to look at something slightly different, but equally important and equally interesting. So let me start with, yeah. So these are some of the details which I also shared the last time, and they continue to remain the same. So this is the first challenge. The point to note here is Prashant Chugh from C.India is the one who is mentoring this particular challenge. The privacy preserving challenge is being mentored by Prashant. If you have any questions beyond what I talk of today, you can of course approach him or you can approach me for further clarifications. So now let me just introduce the topic a little. So we'll start with the key motivations. Why at all are we talking about this and where do we want to take it? So this is the reason why this is needed in countries like India. There is a huge shortage of doctors and the diagnostic centers where these doctors can contribute to the health of the population of the country. That is very, very low. The next slide that I will show shortly gives you some real numbers from a year ago. And you will notice that this shortage is quite bad in some of the states. So assuming that it will take a large number of years to correct that shortage, what is the other thing that one can do? So this is where remote diagnosis starts playing a role. And the reason why remote diagnostics can play a role is because, one, there have been certain advances in artificial intelligence worldwide, and they have shown very, very promising results in disease diagnosis. So this is a positive point. If you can do AI and you can use it for diagnosis, you don't really need a doctor to travel to remote locations or to locations which are at this point in time not covered by trained doctors. And then the other thing that's happening is that there's an increasing penetration of networks into faraway areas, areas which typically do not have infrastructure of any kind. So earlier, they did not have data connectivity and they continue to have shortage of doctors. But now, since they have reasonably high bandwidth connectivity, we can leverage some of that along with the advances in AI to do remote diagnosis of diseases and overcome this problem of shortage to some degree. Besides this, there is a third driver in this space. The third driver is rapid advances in medical diagnostics IoT. So lots of sensors are being developed and these sensors are reasonably priced and they are easy to disperse throughout the country and therefore can collect the kind of data that is required for medical diagnosis. And finally, while the technology is in place, the engineering drivers are in place, there's also the added advantage that COVID-19 has made a lot of governments wake up, including Indian government, and which had already been pushing telemedicine, now looks to push it even more strongly. So you have engineering capability, you have a policy push from the government, and as the first point told us, there is a need because of this huge shortage. So where does this lead us? This leads us to finding a solution that can help service the large population, which is spread out throughout the country. But having said all of this, there are still a few challenges that one will need to overcome to be able to provide these services to the masses. And two of those are, the first is that there is this lack of medical data and records for AI modeling. And this is a problem that exists throughout the world, but it is even more acute in countries like India. So places where you find shortage of doctors and diagnostic centers, you also find shortage of people who collect data in a manner that it can be suitably utilized. So this problem will still need to be tackled if we want to have a usable and acceptable method for remote diagnosis. And the second challenge is not just regulatory compliance, even otherwise, privacy of medical records is something that has to be addressed before anything that talks about remote diagnostics of disease becomes a reality. It may be true that a large number of people in India are not aware of their right to privacy. Yet, there are regulatory requirements so that these boundaries are not transcended. And for these reasons, a remote diagnosis capability will find widespread applicability only if it can provide privacy of medical data records. So in summary, there are two challenges that need to be solved for countries like India for the shortage of doctors and medical diagnostic centers becoming a reality. First is a mechanism for collecting better data, a mechanism for transcribing a lot of already available medical data, and finally ensuring the privacy of the medical data records. If you can solve these two challenges, then all the engineering drivers that have grown over the last few years can be leveraged to provide medical diagnostic facilities that to a great extent mitigate the shortage of doctors problem that exists in countries like India. So with this background, let us look at a few numbers. And these are some of the numbers that give you the level of problem that we are facing here. WHO recommends that there should be one doctor for 1,000 patients. The Indian average is 10 times worse, one doctor for 11,000 patients. But look at the numbers for states like Bihar. You have one doctor for 28,000 people, and this is as of 2018. So the point that we must note here is that there is a huge difference between an optimal number of doctors for the population of the size of a country like India versus the actual number of doctors which are available. What is, is to be noted is that Delhi is a city-state, a small city. It is also the capital of the country. And even in Delhi, you have only 2,000 people serviced by a single doctor on an average, which is twice as bad as what WHO recommends. So Delhi is as good as it gets. It's a city-state, and it is also the capital of the country. And even Delhi struggles to reach the recommended levels that WHO talks about. So this gives us an idea of the kind of problem that we are faced with. But like I mentioned in the previous slide, all is not lost, because the huge advances that we've made in the area of AI and communication, and continue to do so, can be leveraged to provide remote medical diagnosis, provided there are two problems that we overcome. Now here, the first driver, like I said, was advances in artificial intelligence, and these advances are happening worldwide. Even in countries which have enough doctors, they are putting a lot of reliance on artificial intelligence techniques for diagnosis of diseases. And excellent results have been seen in diabetic retinopathy, in tuberculosis, breast cancer, brain tumors, to name a few. And you have examples of studies from throughout the world where extremely good results have been obtained. This, what we see here on the left, talks about a study from Stanford Medicine where AI is rivaling radiologists in screening X-rays for certain diseases. So AI as of today has reached levels of some of the top radiologists in the world, which is saying a lot. So when you talk about remote medical diagnosis, it's not in any sense a compromise. You still end up getting diagnosis which compares with the best that you can get possibly anywhere in the world. So what you're able to do here is provide the best possible diagnosis to the people who have thus far not been able to get it. The other, okay, now the problem here, of course, is that medical data records or data records in general are the bloodline of AI modeling. AI modeling works only if you have large amount of data and this data is correctly curated and correctly annotated. In case the ground truth values labels are incorrect, or if the data has not been correctly or sufficiently recorded, you will run into problems when you try to train the AI model. And because of this reason, it is very important even in the medical domain that you have good quality, complete medical data records along with good quality labeling. However, this is not really the case. The data sets are limited. Then the data sets do not have enough diversity. And what is happening is only a few institutions, only a few geographic regions, only a few patient demographies are the ones that are being covered in these collections of data records. And as we all know, any of us who's worked in AI modeling knows that when you have such biases, you could end up training the models incorrectly. And then what happens is that you might have healthcare centers which have lots and lots of archives. However, these data sources are kept in silos. So they have that data, but they don't readily share it with other such institutes. So even in places where you have the data available, you do not have access to that data, which is same as not having data in the first place. Now, to make matters worse, while there is not enough data, while you, at places where you have data, you don't share it enough, there is this problem that is already starting to trouble the few efforts that are being made to make to share this available. So there are frequent security breaches of medical data. Now this leads to a penalty, but more importantly, it leads to loss of reputation, which means that the other person will be even more careful in sharing data, and people whose data it is will be even more careful about allowing sharing of such data. And now what this does is that security breaches make this grim picture of medical data records even worse. So this is something that needs to be overcome for making medical data records easily available. Now, added to this is the problem of privacy. Now, losing data is bad enough, or data breaches are bad enough, but if the privacy is lost in the process, that makes the whole thing even worse. So there are regulatory compliances, but even if you forget the regulation, privacy is a fundamental right of every human being, and therefore one has to be very, very careful about the privacy of the people whose medical data records we make available for AI medical diagnosis. So on the one hand, you have a poor quality and quantity of data, and whatever little data that you have is being poorly or negatively impacted by security breaches. You also have this requirement of privacy. So all of this, what all of this does is that there is a need to collect a lot more data. There is a need to share a lot more data, but you do this very, very carefully in the sense that the privacy has to be preserved. And this is what this challenge is about. This challenge is about exploiting the increased penetration and bandwidth of data networks. It's about exploiting the advances in medical diagnostic tools and the policy push in telemedicine to come up with privacy preserving techniques for AI. So let me just spend a couple of minutes on these two slides before I come to the challenge specifically. Now, this is a huge driver because for two reasons. One is to be able to share your medical record, you should be connected to a server that contains the capability to perform remote diagnosis. And the second thing is, if you want to collect large quantities of data, a large number of people in your population should be connected. And increasing penetration and increasing bandwidth of data networks in countries like India is making this possible. And India has been very strongly pushing this, not just in urban areas, but also in rural and remote areas. These have traditionally been grossly underserviced, but that will change with the advent of the thrusts that the government is putting on connecting every last person in our population. 5G could make it even better, because in 5G, there are certain ways in which people are addressing remote specifically. And in 6G, there's talk of making remote connectivity a part of the overall standards. So there's a very, very clear move towards ensuring that everybody is provided with reasonably quality bandwidth. And this will be a huge driver in AI-based medical diagnosis. And then the other thing that's extremely important is you can collect this data, you can share this data, and you can give your data to a server that can perform medical diagnosis. But where does this data come from? This data is generated by medical devices which are IoT enabled, so that you perform the sensing on the body of the patient or the person who wants the diagnosis, and this data should reach quickly, and it should be, and of course, while it's privacy preserving, to a server which can perform whatever diagnosis is needed. So there are typically 4 categories of network medical devices. There are consumer products for health monitoring, the smart watches or the smart bands. Then there are wearable external medical devices for specific conditions. Then there are internally embedded medical devices embedded inside the body of a patient. And then finally, there are stationary medical devices in the close proximity of the person in question. And all 4 of these categories of devices can sense data which is necessary and also communicate this data to a server that contains the AI model that can perform remote diagnosis. Finally, the government is not blind to this requirement. Not only does the government realize that increasing number of doctors and increasing the number of diagnostic centers is time consuming. Even though they are working on it, they know that this will take time. So there is a clear push on telemedicine, because if you can enable telemedicine, then you bring a large unrepresented population the services that are available to the few who live in urban areas, specifically the top cities of the country. Now, this is what it is about, this challenge. This challenge is about privacy preserving. Let us make no mistake, even if a lot of patients in India today do not understand the value of privacy, it is not something that can be overlooked even in the developing world. So the technique has necessarily got to be privacy preserving. So this challenge is about privacy preserving techniques for AI. So here what we want to do is we want to collect enough data. We want to come up with AI algorithms which do not require personal identifiable information and still come up with highly accurate medical diagnosis. So there are a few techniques which are suggested, but these are no means the only techniques we encourage the participants to use. You could use a combination of these, you could use one of these, or you could use something else. So there's homomorphic encryption, there's federated learning, there's differential policy, there's secure multi-party computation. And let me just take a few minutes talking about each. In homomorphic encryption, what you're trying to do is you want to, so this is an encryption technique where the functions can be computed on the encrypted data. The encryption is such a mapping that while you encrypt the data, whatever key parameters that you're looking for are not lost. Even after the encryption, that information is still available. So if you want to perform medical diagnosis, you will be able to. So the data owner, what the data owner can do is he or she can encrypt the data with a unique private key. And once that is done, the personal data remains secure, but the AI model is trained to work on that encrypted data, and it will give you accurate results without compromising the identity of the person in question. And then you have federated learning. Now, when you talk of federated learning, what this means is you do not let one person know everything about the record. So if the data record is broken up into different parts, it's fragmented into different parts. The sum of parts will give you the total information that you need, but no single part can derive personal information about the patient. So what federated learning does is, because it's a technique for training machine learning algorithms on private fragmented data, which is stored on distributed servers and devices, no single server can extract the information, enough information to compromise the identity of the person whose data is under question. So this technique, what it does is decentralizes the deep learning, and since the data is not being pooled at a single place, the possibility of it being compromised reduces. So, so the steps involved in such a method is that you train the same algorithm at multiple distributed locations, and the algorithm parameters and not the data is pooled in a central server. And because it's pooled, the diagnosis is accurate, but because the analysis is done in a federated or fragmented manner, there is no danger of compromising the privacy or the identity of the person who's talked about it. Then here are examples of federated learning, a couple of illustrations. So in one case, you have a large number of distributed devices, such as mobile phones, and a lot of data flows in from all of them, and you end up doing distributed training. So you do not know whose data you got, but you got a large amount of data and you're able to do medical diagnosis. The other scenario is you have a large number of distributed devices, and each one of them has large quantity of private data. This is a spelling mistake here, private data, and that private data is trained individually, and individual inferences are then aggregated in a central server to give you the final result. Then there is something known as a differential policy. This is about injecting a small amount of noise. The amount of noise should be large enough so that it becomes difficult for malicious actors to extract the identity, but the noise is not so much that it causes the error, causes an error in the medical diagnosis. So privacy and recommendation are two conflicting requirements. The more information that you reveal about yourself, possibility of a more accurate diagnosis increases, but so does the possibility of compromising your privacy. So noisy data, so differential privacy is a mechanism where you add noise so that you make it difficult to extract privacy related information, but you do not inject so much noise that it becomes difficult to perform accurate medical diagnosis. And it is not, heuristics. Differential privacy provides a mathematically provable guarantee of privacy protection against a wide range of privacy attacks. And you can also have measures on the accuracy loss that such differential privacy mechanisms cause. So you could have centralized differential privacy where you give data which contains privacy information, and then you add noise to it. And the other approach is local differential privacy, where when the person shares his data, it already has some level of noise, and therefore nobody ever sees his or her real data. Both of these mechanisms ensure that the privacy is not compromised. And then there is secure multi-party computation. This goes a step further from federated learning. This makes it even tougher for, not only do you do multi-party computation, but you also encrypt. So what is happening here is that private data is split into several smaller parts, and each part is sent to a separate independent server, and each server processes only a small amount of data, and all of this information is encrypted. So there's a second level of privacy or protection that is provided. So what happens is that you end up with higher privacy, but at the cost of higher computational cost. So if you want a slightly lower computational cost, but that would lead to a slight reduction in the level of privacy you provide, then you could go to federated learning. Now, here are some things that the participants should keep in mind. They can weigh the advantages and disadvantages of the schemes that we've talked about. They can look at the advantages and limitations of these and other techniques, and then they could combine some of these techniques or propose a new technique or pick up one of these and show them to work differently. The detailed problem statements are already available on the website, and I'm sure some of you have seen it already. Others can go back and look at these after the presentation. And there are some references in this presentation that you might want to look at after this presentation. Now, the other thing is that here, this challenge statement is clearly given in the document, but I repeat here for completeness. What we're saying is that we want the participants to design and implement a suitable privacy preserving AI technique to share patient data records available in multiple distributed patient data repositories, and then use this shared data to train a model for medical diagnosis. This has to be done without compromising the privacy. So you have to be extremely careful. The host, you can host, the trained data on a web server while ensuring patient privacy, and you can implement an easy to use UI based tool on a smartphone to do medical diagnostic inference while the patient privacy is preserved, and the patient can easily log on to this particular application and share the relevant data securely and get accurate medical diagnosis. So you could do any of these, a combination of these or some part of these. So that is what the expectation is. These are further references that you might want to look at when you get the time. And since I have used a large part of my 40 minutes, now I'll use the next 7 to 8 minutes to talk about the other challenge, which is dynamic resource or spectrum access. Now here again, what is happening is spectrum is a limited resource. There's only so much spectrum that is available to for communication. So it has to be used very, very carefully. For this challenge, the mentor is Amit Oberoi, and his email ID is given here. You can, if you have questions about what I talk about in the next few minutes, you can connect to him or you can connect to me. So this is the challenge details on the website, just a link to the URL. And this is just to bring to you, to highlight the fact that dynamic spectrum sharing is something that the standardization itself is looking at very, very carefully. So a few more words about the need for sharing the spectrum. So like I said, spectrum is not an infinite resource; it's a limited resource. There are very few usable bands, and those bands are also a finite bandwidth. So when you have a resource which is limited, you want to use it intelligently. You want to use it optimally. So just because some resource becomes a licensed resource, you cannot not allow other people to use it, because there might be times when the primary users are not making use of that resource. So you cannot let a resource which is so scarcely available lie vacant. So there is this concept of cognitive radio. So you have a radio environment where people are using some spectral bands. You could do two things. You could do spectrum sensing, which tells you where are holes in the spectrum, which means what parts of the spectrum are not being used, and a larger study of spectrum characterization in general, what parts of the spectrum are used more often, at what time, at what location. So you could have local spectrum sensing, and you could have a more global spectrum characterization. Combine it with spectrum mobility, the need for spectrum as it moves from one place to another, from one time to the next, and combine it all for spectrum decision, which will take decisions about spectrum sharing. And if you do it correctly, you will be using the resource more optimally, and therefore there will be more transmitted signals, and your your radio environment will become even more cluttered, and the cycle will repeat. So you'll have to do even more careful analysis of the way the spectrum is being utilized. So essentially you have two kinds of users, primary users and secondary users. And for these two sets of users, there is this talk of opportunistic spectrum access. How do you use the spectrum that can potentially be available to you and is not currently being used by the person who is in some sense, maybe because he bought that service, has the right to use it, but is not using it for whatever reason. So this is a diagram which tells you how resource allocation happens. Irrespective of how resource allocation, you probably have to read a bit of this to be able to come up with the spectrum or resource allocation technique. But this talks about time domain and frequency domain allocation. So you have a 20 megahertz spectrum band, and you have a 100 millisecond window, and it is divided into different allocation blocks. And then you have a concept of resource block, which is quite popular in LTE and is also being extended to 5G. And here you have a combination of subcarriers, which means a set of frequencies, and a subframe, which is a duration. So for a duration, you have some number of subcarriers allocated to you, and you get what is known as a resource block. So these resource blocks are dynamically allocated, and there could be times when they are available. So how can we make better use of these resource blocks, make sure that they are not used for the minimum time possible? Now here is a good reference that you people might want to look up. The reference is given at the bottom of the slide. So here they talk about the 3-layer spectrum opportunity information model. You have something called the spectrum data, which is the distribution of the primary users, which is it is the geographical features, and it is about the spectrum allocation and usage. Then you have something known as spectrum information, which you get, some of which you get from the spectrum data. It is collated into propagation information. It is about primary user spectrum occupancy information, and it is about spectrum management info. And all of this information can be mined, and you can construct knowledge and come up with something known as spectrum knowledge. This is a term that these authors coined. Spectrum knowledge is spectrum on opportunity usability knowledge, spectrum management knowledge, and spectrum access knowledge. And all of this, when you have a lot of this information, spectrum knowledge available for you, then if you look at the top right corner of the slide, you can move from spectrum allocation, which is what is currently being done, to dynamic spectrum management, which is where we are moving towards, to smart spectrum management, which is where we want to reach. And here what you do is you do middle or long-term requirement prediction. So you have static allocation of resources, and then you move to real-time or sub-real-time sensing, and therefore you have dynamic spectrum allocation. But at the top, you have spectrum knowledge, and once you imbibe spectrum knowledge into the ecosystem, you can have smart spectrum management, and here you will have minimum wastage of the spectrum as a resource. Then finally, a few words on 5G. 5G will make this problem even more acute, because you will have huge data rates, therefore large spectrum bands, and you'll have multiple uses. So the heterogeneity is going to increase many-fold, not just in terms of the bands and the underlying technologies, but also in terms of applications. So when you have so much heterogeneity, spectrum knowledge would become even more complex. So there's a huge opportunity here to learn more and more about the usage patterns, about the technology patterns, and about the band patterns, and use it to do optimized spectrum or resource allocation. And what a smart spectrum model is expected to do is that it should collect data, convert it into information, and finally into knowledge. And this knowledge should drive the way spectrum is allocated to the different users who want to use it. In this particular challenge, we expect the participants to go a step further. We expect them to do analysis of user patterns as well. So you're not just looking at patterns of spectrum usage, but users' usage pattern, which means the context of the users. You should also try to mine the information that is contained within the user's needs. And that context can help in decisions for opportunistic access. And what will happen is that the allocation will become even better. So you will still have data, information, and knowledge. All that we are saying is that the data should also try to incorporate user context and not just the network context. And here, this set of information here talks about licensed spectrum. Now, this is a spectrum which is for exclusive use because people have paid money for it. And then there is a shared spectrum where you have paradigms for sharing two spectrum bands. And then finally, there's unlicensed spectrum, which is available for everybody to use if they ensure that they keep to within certain prescriptions of power levels and such other, and interference to the bands that are close to it and certain other regulations. So this is how the entire spectrum is available to the users, and it has to be efficiently and accurately utilized. So the intelligent inputs that we're talking about are location, time, type of user, and this will tell you, and this has to be combined with the available Slack for immediate allocations. Spaces for free access have to be advertised by the user equipments. Low latency and critical missions have to be provided, resources on priority. Previous performances have to be kept a note of. Quality of spectrum spaces based on climatic conditions, locations have to be learned. So these are just examples of the kinds of inputs or data that you will connect and transform first into information and finally into knowledge. And if we were to state the challenge is identifying the key variables for dynamic spectrum allocation. So what are the key variables that people look at today? Can we add to those key variables, and then using those key variables, propose a framework for spectrum allocation based on those key variables. And it will be useful if it is compliant to ORAN and it is in line with the specifications of the standardization that is, so that it can easily be integrated with the solutions that are being engineered. And now, since we are running out of time, I'll run through the next couple of slides quickly. This is a source or a tool that you can use for generating data for conducting experiments if you choose to pick this particular challenge up. And I'll skip this slide. And these are some of the resources in terms of the papers that you might want to read. And these are by no means comprehensive. There are many more very good papers available. Feel free to look the net up and come and use such resources. So this is the final slide I had. Thank you very much. Questions?
Thank you so much, Professor Brajesh, for introducing the two problem statements from the Indian challenge. Now, I would like to invite my colleague, Vishnu, to take over for the Q&A session. So Vishnu, now it's your turn to guide us through the questions that are reigning in the Q&A session.
Yeah, thanks, Thomas. Yes, they are raining. So thanks, Vijay, for that wonderful talk. There are several questions here. But as usual, I am going to take advantage of the situation and ask you one of my questions, which is very favorite. Suppose I am a competitor. I am selecting your challenge, one of these problem statements. How are you going to evaluate? For example, let us take the federated learning approach, which you talked about first. Without I am guessing that let us say if you take the privacy considerations and privacy challenge problems that you mentioned, without the threat analysis, it will be very difficult for you to evaluate these submissions which are coming in. So are you looking at a package with the threat analysis? Which problem what kind of threat I'm trying to solve as a competitor? Is that what you're looking for? And how will you evaluate?
Okay, very good question, Vishnuji. Thank you very much. So to answer that question, in federated learning or any other approach that the participants come up with, we are not looking at securing the network. So we're not worried about the kind of attack. Assuming that the attack does happen, what is the level of privacy that is compromised? So there will be two parameters on which the submissions will be judged. One is the accuracy of medical diagnosis, and the second is the privacy preserving capability, assuming that the data is compromised. How much of privacy is compromised because of that, man in the middle attack or whatever other attack happened? Yeah.
Interesting. Okay, let's take one of the questions just here. What is the role of connectivity? So I think there are several questions around 5G and so on. Could you please talk about the role of 5G connectivity in general? Is it 4G or 5G? Does it matter whether it is 4G, 5G, Wi-Fi or any other technology under IMT 2020? What is the role played by connectivity in both? I think it is your first problem statement.
Yeah, right. So when we talk about connectivity, so 5G in particular, if you talk about, then obviously 5G will be deployed when it is deployed. But as Vishnuji correctly points out, it is about understanding the importance of connectivity or the communication network in these two problems. In the first problem, like I said, connectivity is extremely important because you need connectivity for two reasons. For the first reason is you need to collect large amount of data for making your models more accurate and for keeping your models up to date, current. Because what will happen is that the diseases will change, the kind of input that you receive will change, the sensors will change. So for those reasons, you will have to keep on continually collect data and be able to come up with more and more accurate and stronger privacy preserving mechanisms. So there's a fundamental role that the network plays there. In the other important role that the network plays is that you have to make sure that this diagnosis reaches. So when you want diagnosis, the information that you're sharing reaches a central server and then it comes back to you. So the need for the server exists there as well. So for non-critical problems, you do not need low latency, high bandwidth network. But for certain critical applications, for example, when you're using remote medical diagnosis to get an inputs of an expert in an urban setting because you have another expert in another urban setting, then low latency and high bandwidth become critical. So 5G will enable those kind of applications as well. The second, of course, is totally based on connectivity, 4G and moving beyond to 5G. So that is all about spectrum allocation and resource allocation.
Thank you. I think the second question is also related to your first challenge, that is there any data type restriction like image, text in different formats, or can we use combination of data sets?
Okay, again, see, there is no limit on the kind of data set. So it isn't as if that with telemedicine, certain sensors have sort of been mandated. So we don't really have a mandate for sensors for deployment of telemedicine. Well, at least there's work happening on it, but it's not mandated. So you could use any modality. But my request would be that if you keep the modality simple, the ones that can have that can be deployed in faraway remote places as well, it is better. But if you can solve using images while preserving the privacy, we are okay with that. We are interested in two things: the accuracy and the ability to preserve the privacy. So do not let the choice of modality hinder your contribution to this challenge.
Very good. Thank you so much. I think I'll probably jump to the second challenge that you had and ask another of the question which has been troubling me actually. You mentioned about the decisions and the time scale which you had. I think you had a very nice slide where you had these levels of time scales. So let me ask you this: do you consider this time scale as a parameter for evaluation, like the more real time I am the better I am, or something like that? I mean, when I say I am a competitor. So for example, does it matter at all that I am able to take decisions at TTI level or 1 millisecond level, or does it matter?
Okay. So that is a good question. So there are two types of solutions that we were looking at broadly. One solution was the kind where you have a knowledge, but that knowledge is not really real time. Okay, but the way I made the presentation today, when we talked about data, we talked about static allocation. Then when we talked about real time and sub-real time, we talked about dynamic spectrum allocation. And then we talked about spectrum knowledge. When I mentioned spectrum knowledge, it usually is a given that you're operating at a very fine level of granularity in time. But it is not necessarily the case. You could have very smart spectrum understanding and knowledge for a scenario where you know that certain geographies are very light in the night, and some heavy tasks for people who cannot spend as much, you could get it. So they could be non-real time, but even though it appears that it should be non-real time, but knowledge can also be enhanced knowledge for some not so quickly changing scenarios as well.
Interesting. Okay. I'm going to jump and to the end. There are some very interesting questions. How do you describe ORAN architecture for enabling AI ML? I guess let me generalize this question. So, how do you, as a participant, do you look for, what do you look for when you say ORAN based? I think that's the term that you are using, ORAN based. What are you looking for? Are you looking at, let's say I am using one of their interfaces or APIs, or I describe the solution on their terms, or I use one of their simulators? What exactly do you mean by ORAN based?
Right. So first thing, of course, the expectation is that you will use some of their freely available simulators. But secondly, when we say that you stick to 5G or you stick to ORAN, the idea is that in some sense constrains your problem because of the heterogeneity in terms of bands, because of the heterogeneity in terms of applications. It will become an unconstrained problem if we do not define certain boundaries. So you have to use ORAN and not 5G, of course, but ORAN for two reasons. One is for tools on which you will run your solutions, and two, for setting boundaries to what kind of decisions you want to take, what kind of spectrum knowledge you want to generate, and so on and so forth.
Very good. I think let me look at another question from here. is it, should the solution be based on Android alone? I think the question is regarding the first part of the talk about medical data. I see you're shaking your head. Yeah.
So you know, something like Android is not the limiting factor. You could use any platform. So you could use iOS, but we are expecting something. A user interface should typically be, you know, it would be better if you can demo it on a phone. So you could use iOS, for example. But even if you demo it on a laptop, but come up with a mechanism for you know, making it demoable. So we should be okay with it. See, again, the focus is not how well you understand Android or how well you understand iOS. The idea is, do you understand the fact that these are the parameters that have to be sensed? This is how these parameters have to be, you know, privatized, and this is how the privatized information can give you accurate diagnosis. That is what we are trying to find out here.
Very good, thank you. There is still some more questions on how do you, what is the advantage, disadvantage of privacy preserving? What does it mean to provide advantage or disadvantage of privacy preserving methods? How do I propose the best? Is it possible to propose the best? Okay. And what is the assumption on size of data, etc., etc. So I guess there is still there are some questions around how do you test it, how do you evaluate it, and how do I submit it?
So good. So that good that somebody asked this question. So let me take the second part first, where he says that isn't it enough to propose the best? So now the thing is, unless there is a mandated privacy level that somebody talks of, there is no concept of best. What I tried to mention in the talk was that there is a trade-off between the amount of privacy that you can introduce and the amount of accuracy that you can achieve. While you will experiment, those of you who take this challenge up, they will realize that there is a trade-off between the two. If you reduce the privacy constraint, you will get more accurate results, which on the other hand means that as you increase the levels of privacy, the accuracy will go down. So again, there are two things that, best that have to be mandated. One best is the worst accuracy that a doctor can prescribe. He says, if your system gives me a medical diagnosis accuracy which is lower than this, it is unacceptable. And in privacy, the government can mandate that if your privacy is lower than this threshold, then I don't allow your method. Those numbers are not available, so which is good for you in a way, because we do not expect you to reach a certain level of privacy. What you can do is say that, you know, this is the level of privacy I achieved with this accuracy, and if I tune a few parameters, I can move the two scales a little.
Very good, thank you so much. There is the question which we discussed on Friday, the similar question about tool sets. So I'm going to ask you the same question again. Which is your favorite tool set? I know your answer. I know your answer, but I think you should repeat it. And also about something about a non-disclosure agreement for the code that is being submitted. I guess this is something which we can clarify offline. Maybe perhaps we can do that through the website. But your views on the tool set and any restrictions on the code.
So here, let me talk about the tool set first, because you know, there might be some ambiguity there. So we have talked about some tool sets in this slide. We have talked about some tool sets in the document, but those are by no means constraining tool sets. You can use other freely available tool sets, and any freely available tool set or the ones mentioned in our presentations or document are allowed in this challenge. And about the code, of course, it's better that Vishnuji you answer, because that's across challenges, it's consistent, right? So the NDA issue.
Sure, sure. Yeah, I think that's something which we can clarify it offline. So we will update our website and we can handle that offline. I think there is another question on 5G network ready and running. I think you already clarified that. Data sets to use, which data sets to use? I think in your website as well as your PPT, you had several links. Do you want to clarify anything else?
No, just that. So the data sets that are available on the slide set, in the slide set and on the site in the document, you can use any of those data sets. And again, you can use other freely available data sets also.
Okay, very good. In that case, I'm going to ask one last question, which is probably lingering in my mind, which is that the sharing of data. I think you had something very, very interesting about between different, I think you were talking about hospitals or facilities which has data about different parts of the problem, and you were talking about sharing of data. The question which just crossed my mind several times is that will it really happen? I mean, at whose interest is it to share data? Would that really happen? In some sense, it is quite analogous to the code sharing also, right? Open source also. But let me ask your views because you talked about it in your problem statement.
So Vishnu, that is absolutely right. So because in today's world, information, data is very, very, very valuable. Nobody shares that data. But what is going to happen over time is that certain kinds of data sharing will be mandated. What is going to happen is that just as governments work towards moving away from monopoly, they work towards providing the best services to the population. Just for example, number portability. If you're not happy with your you can keep the same number, move to another service provider. Similarly, some amount of data that the hospitals collect will at some point in time, I feel, be mandated by the government to be shared with the patient. So the patient will have some subset of his data always available for him.
Very interesting. There is one last question which says which level of auto diagnose we need to implement. I guess the question is about what level of diagnosis. So we talked about it on Friday, right? You have driver assistance, scene analysis, or is it complete auto driving Tesla that we are talking about? I guess this is a similar question, right? Do you assist the doctor by giving some recommendations, or do you kind of treat the patient using AI? I guess that's the question. It says complete diagnose like a doctor or summarized one by analyzing data model. So I guess the question is that what level of autonomy to the AI are we talking about?
Yeah, okay, Vishnuji, there are two parts to this actually. Of course, there's this level of autonomy. So level of autonomy, of course, is nothing because there's no doctor in the loop. They only have to give recommendations. But I think, this is a problem that we struggle with. So the work that we are doing, for example, on TB data from chest X-rays, there are levels of support that we can provide. One level of support is a diagnosis where you say that this person is TB positive, this person is TB negative, this person has some affliction in his lungs, but it's not TB. So we do 3-level diagnosis. What happens is the next level of diagnosis is generating heat maps of the lung and showing that this part is where you should look for a certain type of artifact. So when you have a doctor in the loop, the doctor looks for certain artifacts in the lungs. So what happens is if you have hard decisions such as TB, no TB, or a problem but not TB, then you have given away that soft information. So we are looking for that hard remote diagnosis. If these people are able to do soft level. So for example, if they can generate a heat map along with the final diagnosis, that is good to have, but that is not what is expected in this particular thing, because we were looking for sensors, privacy and accuracy. We are not looking for driver assistance right now. Sorry, not the driver assistant, doctor assistant. So we want remote medical diagnosis. So we do not want details of what might be going wrong. For this challenge, it is suffice to give a final medical diagnosis.